Hello, uh, this is Charles, and I'm very happy today to share with you our experience of developing and deploying static analysis in big companies, enterprise scale, for the past 5 years. And this is a joint work with my former research group, which are now end group engineers. So the first question you might have is that what is Pinpoint? Pinpoint is actually a static analysis platform that we developed for finding common software bugs such as MPDs, memory leaks, etc. So the project started in 2015, roughly 5 years ago. And 2 years later, we founded the Sourcebrella, which was acquired by the N Group in 2019. And in case you don't know, N Group is the fintech company that is responsible for electronic payment systems, Alipay. Okay, and the reason I think why I'm invited to share is probably because we made some visible contributions in both theory and practice. So we not only that we published many innovations in terms of top academic papers in top PL and software engineering conferences. Well, we also have deployed our ideas in almost all leading Chinese technology firms, such as Ant, WeChat, Huawei, Baidu, etc. And it's particularly remarkable that the entire C and C++ repository of Baidu, which is the Chinese Google, is being scanned by Pinpoint every day. So, and we're still having a lot of new ideas and new innovations in collaboration with the people in the N Group in pushing static analysis forward. So before the official content of the talk, I'd like to set some liabilities. First of all, I'm talking about static analysis proper, right? So I'm talking about try to extract some kind of model, semantic model, and try to predict the behavior of software systems, which means in case, for example, if you work in the area of mining repositories, many of my observations or conclusions might not apply. And then I'm talking about checking strongly typed languages, C and C++. So don't ask me any question about JavaScript. We're still figuring it out. And the second, I'm talking about systems that are very big, over a million lines of code. So these are the systems that are willing to need static analysis, first of all, and willing to invest heavily on this technology. And also, you will find that most of my materials tend to be very practical because we think about developers are the direct clients of our innovations. So, which means that I don't deny the importance of any theoretical breakthroughs, but I tend to look at the more practical side of technology, right? How it serves developers directly. And the structure of my presentation, it follows the usual rhetoric of any academic paper. So in an academic paper, we first try to outline the problem. So our problems is that there are many new characteristics of modern software systems. And then we have a research goal, right? So our renewed research goal is what I call the DORA enterprise scale static analysis principles. And you probably guessed right. I coined this name according to the favorite cartoon character of my daughter. And then we present a motivation in criticizing all the past research is inadequate. Okay, and then I present a solution. So if you write research papers, you should be very familiar with this structure. So the first part is that I want to present some new observations, maybe not new observations, but the kind of characteristics that we would like to address for the so-called modern software, or enterprise scale software. And the first characteristic is that modern software, or the software systems of our clients, tend to be very big. So we're talking about 1 million lines of code as the minimum, as the norm. I cannot share with you the actual sizes of our client systems, but I found some data online, and this is very representative. Even for consumer products such as car, the size of software can reach 100 million lines of code. So these systems are very, very big. Even these small things, IoT things, are also big. We're talking about still around 1 million lines of code to analyze for these systems. So the kind of systems that we deal with are not only very big, but also alive, right? So what I mean is that, for example, one of our client systems are having over 100 major revision every day. Same happened to other popular systems. In 2018, we did a study that, for example, Linux kernel has 9 commits per hour, Clang, TensorFlow of the similar frequency, similar scale. Which means that we're not dealing with a stationary target, we're dealing with a moving target. Modern software increasingly developed out of the house or assembled from suppliers, which we call a software supply chain problem. So in this report, 2016, it already indicates that from 15% to 30% of all systems are acquired from commercial third parties, which means that you likely don't have any source code that come with it. And also this recent evolution into the cloud actually has the same characteristics. For example, in Amazon Lambda deployment, the maximum size of any deployed system is just around 25 megabytes. So this means that most of the functionality come from outside, and what's worse, these functionalities don't have source code that come with it. So this problem I refer to as the dark code problem. Software not only mostly assembled, they are being pocketized. All right. So again, with this push of cloud-based deployment, developers now try to decompose big and monolithic systems into many smaller components that talk to each other via strange ways, right? So via callbacks, via IPCs. So there are good reasons for doing this, to increase fault tolerance, to increase elasticity. But this poses new challenges for doing static analysis, because program control flow, if you break things apart, cannot no longer be locally reasoned. Okay, so the flow is becoming what I call reactive instead of imperative. And there's a lot of dependencies, either data dependency or control dependency over the network, right? Over some kind of IPC mechanisms. So this is also interesting. And in addition, the kind of systems that our clients from our clients are not only being tested heavily on the binaries, they're also being tested heavily on the source. So what I mean by that is there are a lot of things, a lot of source level scrutinization that needs to be performed. Things like coding standards, right? So for example, British government have this coding security standard on all Huawei products, okay? And also there are coding standards of sectors, right? So avionics, autonomous driving, they all have their own coding standards that's being heavily checked and needs to conform to. And there are a large number of user-specific specific queries or requirements on the source code. Examples like status code, propagation problems, security attack simulation, impact analysis, code search queries. So there's a lot of what I call testing, or a lot of interests are on the source code itself, and it's very, very diversified. So these are the characteristics that arise when we deal with our customers. And as we look back, what do all this mean to static analysis, right? So how to get your static analysis adopted by companies, or by practitioners? I guess to get your child adopted, we have a list of things that we must do. So first of all, your technique cannot produce a lot of false positives. I guess this is very straightforward. And also, your technique needs to be very fast, right? So I'll talk about that more later. So not only that, your system, you have to do all that, right? So low false positive, very quick scan or analysis, but when the source code is constantly changing, okay? We must have some kind of assumption of the dark code, because most, maybe in the next system, most of the code is no longer available in source code. And we have to have some degree of understanding of this non-local program dependency, right? Over callbacks, either callbacks from frameworks, event handlers, or other IPC mechanisms. And we must allow user to define their own analysis, right? So these are the criteria that a good static analysis must satisfy in order for our clients to adopt. So when we design the static analysis techniques, I think this is a set of requirements that we try to satisfy. So first, we want to achieve good performance, because that is the foundation. So by good performance, we mean we give precise results over sound results, right? We want to give very few results that are reasonably well, instead of giving a lot of false positives. And we need to be fast. So the fast, I think there is a boundary for being fast. You can be as fast as editor feedback. So when developer click the save button, you already have the result back, and as long as nightly build, right? So if your results is delivered several days after the code is being modified, we found that it gives a heavy burden, heavy memory load to developers in order to remember what he did and try to understand the bug report. So these reports are valuable reports. I admit it's hard to achieve true positive results, but these results are valuable, meaning that they understand program flow, they understand the context, and they understand the path. Okay, so they're reasonably precise. So being precise and fast, and then we have to aim for this DOR principle. Okay, so we have a reasonable assumption of the dark code. We must be open for customization through APIs or DSLs, and we must understand reactive control flow, and the analysis itself needs to be asynchronous, right? So the whole analysis can be carried out in different space and time, and then we can piece these results together. So this is different from compositional, because compositional is one way to achieve this so-called asynchronous analysis. But in any ways, we need to accommodate results that come from different parts of the analysis time and space. And the real horror story is that we have to achieve all of them simultaneously. Or else, I think static analysis might be irrelevant in a sense that it is getting more difficult for practitioners to really adopt your technique. So as an academic researcher, the natural reaction is, of course, when you see a problem, you try to find what people have already done to address these problems. And to answer that question, my own intuition is that I didn't see a lot of work to address all these factors in combination, so I took a very audacious feat of looking at all research in the past 15 years. So all research means that I picked all the conference, the top PL and the software engineering conferences that ranked high by our department standards. Okay, so again, this is purely subjective. If your favorite conference is not on the list, it's not intentional, so it's maybe a small sample of the whole big picture. So the criteria is we try to look at all these static analysis papers. By static analysis papers, like I said earlier, we talk about extracting some models from the source code, not just parse its tokens. And then we look at the size of the subjects that gets evaluated in these papers, and also how the paper address this DORA principle. And the answer is probably expected, is that if I stack them, so this is the metrics of all the papers, the columns are each paper, the columns are papers, the rows are how they address these DORA principles, and I stack them together in one picture. And it's a pretty sparse matrix, which means most of the paper don't address any of these principles. Okay, so here are some detailed observations. I think static analysis is still a very active research area. So roughly for all these conferences, there's one static analysis published for every 20 papers. So I don't know if it's very active, but I think it's active. And for these papers that are about static analysis, the only 3% of them address code size of 1 million lines of code. Remember, I said earlier, the minimum size our client systems is 1 million lines of code. Okay, but majority of these papers address sizes between 10K and 500K lines of code. In terms of DORA principle, we found a significant portion of these papers address these principles. So, for example, there's 7% of the papers address asynchronous analysis, 10% addresses reactive control flow, so on and so forth. So this means I didn't invent these problems. These problems are important problems that people look at. But the real problem is that only 4% of all these papers address 2 criteria simultaneously. And no paper address more than 2. Okay, so which means the combination of these problems become a new problem. And I think that major breakthroughs are still possible if you consider addressing these problems in combination, just not individually, but address them in combination. But another conclusion is that there's really very little experience we can draw, at least from my own perspective, we can draw from past research to address DORA problems in combination. So we also looked at a little deeper in terms of major design frameworks to see if there are any inherent limitations. So we looked at 4 major schools of approaches for static analysis. Again, this is very subjective, and if your favorite one is not here, we can probably discuss it later on. But these 4 frameworks are IFDS, symbolic execution, by abductive reasoning, and sparse value flow analysis. So let's look at these major categories in turn. And so I guess one of the most influential framework for static analysis is FDS IDE. I guess everyone probably know about this already. So the major breakthrough of this is that it can be more scalable and precise because it converts a sort of iterative lattice-based approach into a graph, a search problem on a graph, right? So which is much more efficient. You can do this by focusing on a subset of data flow problems, which are called distributive problems. Okay, so this is pretty influential. But when we consider it, there is one thing that we are very concerned, which is that a lot of problems actually are non-distributive, especially pointers. Okay, so which can cause precision problems, great precision problems for FDS. And another factor is that we cannot figure out how to encode path sensitivity in the FDS framework. And also, since it is a framework, it needs to be instantiated with a particular kinds of data flow facts. We have very limited knowledge of how it can be customizable of different data flow facts, right? So this framework needs to be instantiated individually for different data flow problems. But what we want is a more general, open, and customizable solution. So we kind of got cold feet in going in this direction. So next one we examined is symbolic execution. I guess here is pretty obvious that symbolic execution is very precise and versatile. It can solve a large category of problems. It has no path explosion. It's path sensitive. It doesn't have this pointer problem because you can just strongly update the pointers along the execution. But I guess most of us agree that there are limited evidence for symbolic execution to scale to code sizes over 1 million lines or even tens of millions of lines. We don't know how to do it either. And next we look at by abduction. So we like this approach a lot because it doesn't need a separate pointer analysis. Okay, so and the design itself is very asynchronous. It allows the summary to be built and to be kept separately, and then you can compose everything together later on. But what we are concerned about by abduction is its limited precision and scalability. It has very limited path sensitivity whenever the path variables will collude with the preconditions that it try to use in its inference formula. In its small spec goal, or the weakest precondition criteria will actually generate simpler preconditions that allow the imprecision to propagate as it performs the bottom-up inlining. And the separation logic solver, we feel, is not as mature as SAT. So, and also you need to write manually specified pre and post conditions for at least for leaf functions. And they are problem specific, so we have concerns about how easy it is to customize this framework for different bots. So we didn't go that direction either for these reasons. The last one we examined was called sparse value flow. And the idea is pretty simple. I think it's a database approach that try to index the data flow before the actual query happens, right? So we try to build data dependence graph as an indexing technique. And then it's pretty versatile. So if any source sink based problems, you can also encode on this so-called the sparse value flow graph. And it's graph-based, so it's very easy to encode path sensitivity, and the whole analysis is on demand. Okay, so no exhaustive approach. Exhaustive approach doesn't work for large systems. But traditional sparse value flow has this problem we called the pointer trap. We think that it's similar to FDS. Actually, for it to work, it needs a separate whole program data dependence analysis. And this is the killer. Because if you want to do a very precise data dependence analysis, you need to have a very expensive points to analysis, which actually make it non-practical for big systems. So in fact, many approaches uses very cheap points to analysis to build as a pre-analysis, as a separate stage. But this actually bring down the precision and scalability dramatically because many edges are polluted. So as for the solution that we developed, we actually built on top of sparse value flow analysis. We like the fact that we can use graphs. The whole analysis is on demand. And we have this sparseness that we think this combination is the best compromise to address all sensitive paths, context, flow, all sensitive analysis for very large systems. Okay. It has its limitations, but we think these three characteristics are very attractive. But different from the traditional sparse value flow analysis, our approach, we don't require a prior knowledge of complete data dependence. In a sense that everything is on demand, including pointers. Okay, so for each bug query, we construct a feasibility, all sensitive feasibility query containing both values and pointers. Okay. So how do we achieve that? It's detailedly documented in our PLDI 18 paper, but to give you some high-level picture, here are some basic steps. The first step is called a purification step. That is, we perform a very precise local data dependence analysis to summarize the I/O effects. So this means the input and the output, including the effects, the I/O affected by the pointers. Okay, so we discover all these effects, and the next thing that we go to its color. In its color, we create a lot of symbolic variables to represent these side effects, the I/O effects, including input and output, and including the side effects. So we did a transformation of the color, and then we performed the same degree of local high precision local data dependence analysis on the color. And then we transform its color recursively. Okay. So in the end, every function has this graph that basically is the routes for value flow. It doesn't matter if those values are real values, scalar values, or real values. Okay, so in terms of finding the actual bug, the procedure is a standard SVF procedure. We start from the bug predicate, and then we going backwards and try to reason about the feasibility of the path. But we also have some additional measure try to alleviate the load of the SMT solvers. We have some simple decision procedures to find very apparent contradictions in the feasibility query so that we don't send it to the SMT solver. And this picture gives you the architecture for Pinpoint. Basically, it is based on LLVM bytecode, and we have some front end that translate different language front ends into LLVM bytecode, and we have some normalization procedure, and finally generate our intermediate representation, which are called SEG or UFG, which can be stored in the disk as well. And our backend defect analysis rules are actually independent of the language front end, and then which means we can actually perform multi-language analysis and also cross-language analysis, such as analyzing native code together with the Java code. So there are some other key contributions in Pinpoint other than the basic algorithm published in PLDI. And we also published the type state analysis in XC19. And also we have dramatically improved the analysis speed of the engine. So we have some trick of doing pipelining and also accelerating the SMT searching process. And also to address this issue of customization, we have some ideas of how to optimize the performance when you have a lot of checkers or a lot of bug finding algorithms that to be carried out at the same time. We have also have some ideas there. In terms of its performance, so Pinpoint can actually simultaneously check 40 different bugs for 8 million lines of code. So this is the benchmark we used in our PLDI paper report. But now we can do the same, perform the same task using half of the time reported in PLDI. So now we can do it in 2 hours. We have found over 80 bugs in the and 4 of them are very critical that are assigned CVEs. These bugs are found in very popular open source systems. So by very popular, I mean that these systems are frequently scanned by a number of open source and commercial static analysis bug finding tools. Of course, we found thousands of confirmed bugs in private systems. That's why some company want to buy us. To give you some example of the kind of bugs that Pinpoint can find. So this is one of the bugs in the MySQL, and this bug is found in a 1,000 lines function. Pretty hard for human to inspect. And to find this bug, Pinpoint actually reasoned about 36 functions, 11 compilation units. So the bug itself is quite complicated. It's so complicated that it's really hard for human to comprehend. That's why this bug went through 3 rounds of confirmation. So for the first 2 rounds, they did some analysis, manually inspection, but couldn't confirm. Only in the 3rd round, when they used a dynamic method, a debugger, that is able to confirm this bug. So which means that that Pinpoint can actually reason, in this case, very sophisticated reasoning that used to be, to find the problems that probably can only be found by dynamic methods such as testing. And this bug is another bug that's been hidden inside a critical unit for handling Unicode for 10 years. And affected hundreds of organizations, and then it was assigned a CVE ID. So this shows that Pinpoint can really find bugs that are very difficult to discover. And among many other recent advances of Pinpoint, for the time limitation, I picked a particular. Well, I picked the Pinpoint Coyote, which is to speed up the core engine by pipelining the data flow analysis, which I think is very cool. So the ideal is that the throughput of static analyzers are limited by the degree of parallelization. Okay, so this is a graph taken from a FSE paper written by the Coverity guys, and the ideal is that the degree of parallelism is inherently limited by the shape of the tree, of the call graph. Okay, so which means that you can parallelize on the leaf functions, but as you go up on the call graph, the degree of parallelization is limited by the density of the nodes on top. Okay. But we have this idea. So any chance to do better? So we had this idea that when you take a magnifying glass and look at the facts that we're building for each individual function, we found that many data dependencies of these facts are actually independent of each other. Okay, so so that we don't have to wait for the leaf function to completely finish before we can start analyzing the caller. Okay, so whenever the partial facts of the callee is ready, we can start analyzing the dependent facts in the caller. So in a way, depends on how many of these facts are orthogonal or independent of each other, we can actually stack them together in a pipeline to analyze this. So the result is very, very significant. In general, we observe at least twice or three times of speed improvement. So this is significant because in some analysis that's over longer than a nightly build now can be finished in 4 to 6 hours. So an impractical analysis can now be practical. So in conclusion, I've just talked about our experience of getting people to adopt our static analysis algorithm for very large software systems. And for us, enterprise scale or static analysis for big companies means that we need to be precise, we need to be scalable. So we're talking about all sensitive analysis, we're talking about tens of millions of lines of code. And we need to address the DORA principle simultaneously. So if we do that, our tool will instantly sail, right? People will adopt it with no hesitation. And in terms of research for bug finding or verification in general, I think that maybe we should looking at how we can address the DORA principles simultaneously. So otherwise, I think it's getting more difficult for people to adopt our algorithm, our ideas. And there are plenty of opportunities for major breakthroughs. And disclaimer is that Pinpoint is nowhere near addressing DORA principles simultaneously. So we're still on the way. So Pinpoint is a recent attempt. In the first stage, we primarily focused on being precise, being scalable, and being open. And there are ongoing work, for example, using disk to store intermediate analysis results so we can achieve asynchronous analysis. And we also are breaking the monolithic static analysis process apart and using clusters to increase its throughput and, of course, the tolerability to faults. And also we started to look at binary analysis to extract limited binary knowledge to help getting better results for analyzing the rest of the system. So more information can be found on my website in terms of research results, and for Pinpoint, more information you can find on the SourceBrala website. So that is all that I want to share with you at the moment, and I'm looking forward to have a lively discussion with you. Thank you so much for your time.